Hello everyone, I am Dr. Fawzul Atiq. I am giving some series of lecture for the course Probability and Statistics. So in the previous lecture, we have discussed a particular type of continuous random variable, which was uniform random variable. So in today's lecture, we are going to discuss about another continuous random variable, which is known as exponential random variable. What is that? So a continuous random variable whose probability density function is given for some lambda greater than 0 is fx is equal to lambda e power minus lambda x if x greater or equal to 0 or equal to 0 otherwise. And it is said to be exponential random variable, or more simply it is said to be exponentially distributed over with the parameter lambda. Right? So the probability density function involves some exponential function. So fx is equal to lambda e power minus lambda x. So in this case, we call this random variable as exponential random variable. And we can easily verify that yes, it is a positive function, and its the total probability sum is actually 1. So minus infinity to infinity fx dx, what is this value? We can easily see that. So minus infinity, but it is taking value from 0 onwards, so 0 to infinity fx dx, so lambda e power minus lambda x dx. So if you do the integration, lambda can be out, so e power minus lambda x divided by minus lambda, and the limit is between 0 to infinity. So if you put the infinity limit, the e power minus infinity gives you 0, minus e to the power 0 gives 1. So minus 1 was outside, into 0 minus 1 gives you the 1. So it is verified that yes, it is a probability density function. So the variable whose density function is this, you called it as continuous random variable. Now again, like the previous lectures, once you have a new random variable, we'll be talking about its cumulative distribution function, we'll be talking about its mean, variance, all this, and few examples where you can apply this thing. Right? So let us calculate its cumulative distribution function. So it is divided its value between at the point 0, right? So if your a value is less than 0, then what is the cumulative distribution function fa? Definitely it is minus infinity to a, but here fx value is 0, so, or maybe I'll write down minus infinity to a fx dx. But in that interval, because a is less than 0, fx value is 0, so therefore this value is 0. Right? And if you have your a value is greater than or equal to 0, then what is your fa, cumulative distribution function? Again, it is minus infinity to a fx dx. Therefore, it is actually 0 to a fx dx. Because it's anyway fx value is from 0 onwards, it has some non-zero quantity, right? Therefore, I have taken from 0 to a. And a value is greater or equal to 0. So in this range, what is the fx value? So it is 0 to a lambda e power minus lambda x dx. And if you calculate, lambda can be out, then e power minus lambda x divided by minus lambda over the interval 0 to a. And if you calculate, what value you are getting? So minus 1 is outside. If you put a value, so it will be minus lambda a, and if you put 0, so basically you will be finally you are getting 1 minus e to the power minus lambda a. Correct? And if you just write it in a special manner, then your cumulative distribution function is actually this one. If your x is greater or equal to 0, it is 1 minus e power minus lambda x. We calculated for a, then we convert it for, so if a greater or equal to 0, it is 1 minus e to the power minus lambda a. So therefore, if x greater or equal to 0, it is 1 minus e to the power minus lambda x and equal to 0 otherwise. So this is the cumulative distribution function for exponential random variable. Clear? And some probability, why we calculate, because once you know these things, many probability we can directly write with the help of cumulative distribution function, right? So these are also helpful in many cases. Okay, now as I discuss, your next job is to calculate the expectation and variance of this random variable. So to do that, first what we will do, we'll calculate the expectation of x to the power n. And why we'll calculate, we'll see that once you calculate this, we'll actually get it is in terms of some other expectation, and that will helpful to calculate e of x square all. So e of x to the power n is what? So as you know that it is minus infinity to infinity x to the power n fx dx. But that fx value takes from 0 onwards, so it is 0 to infinity x to the power n into lambda e power minus lambda x into dx. Correct? Now what you have to do, we have to again do this integration. What you have to do, you have to do the integration by parts. So where one algebraic function, one exponential function is there. So take x to the power n as a first function. So it will become x to the power n into lambda was there, and integration of these things, it is e to the power minus lambda x divided by minus lambda. It is between 0 to infinity. Then minus integration 0 to infinity derivative of x to the power n, which is n x to the power n minus 1 into integration of this part, so which is lambda into e to the power minus lambda x by minus lambda dx. Now if you put this infinity limit here, e to the power minus lambda x gives you 0. If you put the 0 limit here, x to the power n gives you 0. So 0 minus 0, so this part is actually 0. Correct? And then one minus sign is here, one minus sign is here. So this will become plus. And plus, what should I write? I'm just writing n by lambda. I'm not cancelling out, I'm taking it n by lambda and 0 to infinity x to the power n minus 1 lambda e to the power minus lambda x dx. So I have written intentionally in this form. Lambda I could have cancelled out, but there is some reason. Now could you please see that what is this quantity? Correct. So if you just look at this quantity, it is e of x to the power n. So what is this quantity then? The below one, e of x to the power n minus 1. Clear? So therefore, we can write this is n by lambda expectation of x to the power n minus 1. Now finding expectation and variance is now very easy. Now once you have this recurrence relation, e of x to the power n equal to n by lambda e of x to the power n minus 1. Now let us calculate expectation of x. So e of x, expectation of x, that means x to the power 1. So put n equal to 1, it will become 1 by lambda into e of x to the power 0. X to the power 0 means it is 1. So 1 by lambda e of 1. So expectation of a constant thing is actually 1, that constant number itself. So it is 1 by lambda. So therefore expectation of a exponential random variable with parameter lambda is 1 by lambda. Okay. And the next part is we have to calculate the expectation of x square. So what is e of x square? To get the variance, we need this. So that means n equal to 2. So 2 by lambda expectation of x to the power 2 minus 1. So expectation of x. But expectation of x we already calculated, 2 by lambda into 1 by lambda. So therefore 2 by lambda square. And finally variance is what? E of x square minus ex whole square. So 2 by lambda square minus 1 by lambda square. Therefore this value is 1 by lambda square. I hope it is clear. So therefore the mean or expectation of the exponential random variable is the reciprocal of its parameter, so which is 1 by lambda, and variance is the mean, whatever its mean, which is 1 by lambda, its square, so 1 by lambda square. I hope it is clear. Yeah, so this one we have already done. Then few things about the exponential distribution. So it is very widely used to model the time until a specific event occurs, right? And it is ideal for analyzing waiting times or duration between successive occurrence. It is mostly used in these cases, that the waiting time or duration between two event will occur. So successive occurrence. and it describes the time between events in a Poisson process where events occur at a constant average rate. So event will occur at a constant average rate. Then it describes the time. And what we have seen, the probability of an event happening is decreases exponentially as time progresses because it is lambda e power minus lambda x. So whenever you increase x, so e to the power minus x, it is actually decreasing, right? And how it is decreasing? It is exponentially decreasing. So if you see the graph, you will see it is exponentially, it is decreasing. Therefore, we can make this statement that probability of the event happening is decreases exponentially as time progresses. Now, in which cases we can apply these things? That time until an earthquake occurs, that model the interval between successive earthquake which occurs randomly. It can also estimate the time between successive conflicts in a region, right? It can also model the time until the next incorrect call occurring randomly. So this kind of cases, you can apply this exponential distribution. So it is applicable in the field of geology, politics, communication, and many others. Right? These are few things about the exponential distribution. And now let us solve some example, actually, which is very easy in nature. Suppose that the length of a phone call in minutes is an exponentially random variable with parameter lambda equal to 1 by 2. So length of a phone call in minutes, it is already given. It is an exponential random variable. If someone arrives immediately ahead of you at a public telephone booth, find the probability that you have to wait more than 10 minutes or between 10 to 20 minutes. Now, this is very straightforward example. You can very easily do. So, what is the solution of it? First of all, the probability density function, let us write down. The parameter is lambda equal to 1 by 2, right? And it is exponential random variable. So what is the probability density function? Lambda e power minus lambda x. So it is 1 by 10 e power minus lambda x. So minus x by 10 whenever you have x greater than 0 and equal to 0 otherwise. Right, and then let us calculate the answer. So you have to wait more than 10 minutes. That means what? Probability of x is greater than 10. Now x greater than 10 means it is 10 to infinity fx dx. Actually, you can use the probability density function also to prove this result, to get this answer. Right? But I'm doing this one. The next one, maybe I'll do it with the help of probability density function. So 10 to infinity fx dx, it is therefore 10 to infinity 1 by 10 e power minus x by 10 dx. So 10 is outside, and if you do the integration, it is e to the power minus x by 10 divided by minus 1 by 10, 10 to infinity. So this, there will be a minus 1 here. And if you put x is equal to infinity, e to the power minus infinity gives you 0. So minus e to the power 1. So basically it is e to the power minus 1 if you simplify it. So the first part is done. Then part B is probability of 10 less than x less than 20. So you can do this one as well, that 10 to 20 fx dx, but you have your probability cumulative distribution function also, right? Because we know that cumulative distribution function is what? 1 minus e to the power minus lambda x. If you remember, we have already calculated the cumulative distribution function here, right? So where is that? Yes, 1 minus e to the power minus lambda x whenever x greater equal to 0. We can apply that one. So if you do that, 1 minus e to the power minus lambda x. So this is basically a cumulative distribution function is an antiderivative of fx. So we know in our previous lecture we have seen that it is actually f of 20 minus f of 10. And this value was whenever x greater equal to 0. So we can easily answer this question as well. F of 20 minus f of 10 So what is f of 20? It is 1 minus e to the power lambda is 1 by 10 into x is 20, and then minus f of 10 is what? 1 minus e to the power minus 1 by 10 into 10. And therefore 1 will be cancelled out. This will be plus. So e to the power minus 1. This one will be plus sign and minus e to the power minus 2. So we got this answer. So this is all these things we can do it in two way, right? Either you can use the probability density function, and we have already calculated the cumulative distribution function. You can use that one to guide the probability. So in any method you can use, right? You should be getting the same answer. Yeah, like that. That here in this already a solved answer, I have taken the probability density function. You got the same answer, e to the power minus 1 minus e to the power minus 2. Whereas here I have taken the cumulative distribution function, you got the same answer. So depending on your situation, whenever whatever you feel convenient, you can use that. I hope it is clear. Okay. Now one interesting property we will understand, that memoryless property of exponential distribution. So first of all, let us understand what is a memoryless property. Very, very interesting one. You will see that it's a very easy as well. So a non-negative random variable x is said to be memoryless if for all s comma t greater or equal to 0, probability of x greater than s plus t given that x greater than t is equal to p of x greater than s. What is this sign? It is the conditional probability. What is the condition? X greater than t is given. Then probability of x greater than x plus t is actually equal to p of x greater than s. What does it mean? It means that if x denotes the lifetime of an object, that is a machine or an instrument, then the memoryless property means that given that the object has already survived for t hours, that is the condition, x, that given probability x greater than t, already survived for t hours, then the probability that it survive for an additional s hours, that means p of x is greater than s plus t, right? Then this probability it is same as the probability that it survived for s hours from the beginning. So here the condition x greater than t, it was already survived for t hours, it is actually not taking into the consideration, right? So the object does not remember how long it has been functioning. So whenever you say that x given that x greater than t, probability of x greater than s plus t, it is actually counting that from the beginning whatever its probability from x greater than s, right? So this condition x greater than t, then the additional hours it is working, that what is that probability? It is the same as from the beginning how much it survived for s hours, right? So therefore it is not taking its into its memory that from how long it is functioning. So its remaining lifetime is independent of how long it has already been survived. That means some machine is there, it may survive for 10 years already. Then after 10 years, whatever is the probability that it will break down within 1 year, it is same as that from the beginning, starting onwards, what is the probability that it will break down within 1 year? It is the same, right? That this 10 years it has survived, it don't remember. 10 years it survived, or you may say that total 11 years it survived, given that 10 years is already survived. It is same as it is the probability that how, like, what is the probability that it will survive within more than 1 year also. It is same as like that. Got it? So this is the condition of this memoryless property. Now this condition we can actually make it an equivalent condition. How? So this quantity is actually this one, that p of x greater than s plus t given that x greater than t. It is the conditional probability, right? P probability of a given b, like that. What is the rule, you know? The conditional probability definition: p of a intersection b divided by p of b. So it is same. So p of x intersection greater than s plus t intersection x greater than t divided by p of x greater than t. right? So we have to take the intersection of these two event. Now, can you think of it that what is the intersection of x greater than s plus t and x greater than t? If you understand that x greater than t means what? P of x greater than t means what? It is integration t to infinity fx dx. So can't I write it that t to s plus t fx dx plus s plus t to infinity fx dx? Now what is this value? This is p of x greater than s plus t, right? And therefore if you take the intersection of this, so basically you will be getting this value, right? Because this is already included in x greater than t, right? P of x greater than s plus t is already included in x greater than t. Therefore intersection of x greater than s plus t and x greater than t is actually p of x greater than s plus t divided by p of x greater than t. I hope you understood. Okay, so once you have this thing, then what you can write that this is basically the memoryless property was this one is equal to p of x greater than t, but this value we got it as p of x greater than s plus t divided by px plus t, and therefore we got a new form of the memoryless property, which is p of x greater than s plus t is actually equal to p of x greater than s into p of x greater than t. So this is the equivalent form of the memoryless property, right? So now if some random variable whose probability follows this condition, we called it as it has the memoryless property. Now we can also show that our exponential random variable follows this property. How we can show? What is our this exponential random variable? Now for the exponential random variable, take any k. I am taking any k. K is any positive quantity, any positive real number. What is its probability? So it is k to infinity fx dx. Now what is fx? The density function we know, lambda into e to the power minus lambda t or lambda x dx. We know this value. Now if you calculate, it will be lambda into e power minus lambda x divided by minus lambda and between k to infinity. And if you put the value, infinity will gives you 0 and k will gives you minus lambda k, but it will minus and minus will be plus 2 e to the power minus lambda k. You got this value, right? So p of x greater than k is e to the power minus lambda k. Then if I have this thing, what is p of x greater than s plus t? So another real number s plus t. So it is e to the power minus lambda times s plus t. Now can't I write this as e to the power minus lambda into s into e to the power minus lambda into t? But what is this quantity? E to the power minus lambda is? It is p of x is greater than s. This is what? P of x is greater than t. According to this rule. And therefore we got p of x greater than s plus t is actually equal to p of x greater than s into p of x greater than t. What is that? It is the memoryless properties equivalent form. So therefore, if I have the exponentially distributed random variable, it follows the memoryless property. I hope it is clear. So we understood that an exponentially random variable follows the memoryless property. It has uh, the property that it has the memoryless property. Random variables are exponentially distributed random variables are memoryless. Right. So the future behavior of the system depends only on the present and not on the past because it does not take its memory. And the only exponential distribution in continuous random variable and in case of a discrete random variable, the geometric distribution is also memoryless. If you see its geometric distribution, geometric random variable, for the case of discrete random variable, you can see that P of x greater than s plus t is actually follows that P of x greater than s into P of x greater than t. So in continuous random variable, exponential distribution, in discrete type random variable, geometric distribution, both for have the memoryless property. And this property is useful in reliability queuing theory, where the system forgets how long it has been running. I hope you understand what is this memoryless property, which is very interesting in nature. Now, because we know that the exponentially distributed random variable follows this memoryless property, now we can solve some example very easily without doing much effort. Look at this example. The time in hours required to repair a machine is an exponentially distributed random variable with parameter lambda equal to 1 by 2. Then what is the probability that a repair time exceeds 2 hours? So first of all, let us write the density function. Let x is the this random variable. So the density function of x is fx is equal to, parameter is 1 by lambda. So 1 by 2 e to the power minus x by 2. Whenever you have x is greater or equal to 0 and equal to 0 otherwise. Now the first question, what is the probability that a repair time exceed 2 hours? So this is straightforward, p of x greater than 2. And this is just, if you do the calculation, it is 2 to infinity fx dx, and then 2 to infinity 1 by 2 e to the power minus x by 2 dx. And the same thing we are doing it from the last few minutes. 1 by 2 into minus 2 into e to the power minus x by 2, and integration is between 2 to infinity. If you just simplify it, the 0 minus e to the power minus 1. So it is e to the power minus 1. The first part is done. Now the interesting part is the second one. What is the conditional probability that a repair takes at least 10 hours, given that its duration exceeds 9 hours? Right? What does it mean? Conditional probability that a repair takes at least 10 hours, given that its duration exceeds 9 hours. That means probability of x takes at least 10 hours. That means x is greater than 10. Given that its duration exceeds 9 hours. That means x already crossed 9 hours. So this conditional probability you have to do. Now this one, can't I write it in the form that x is greater than 9 plus 1, given that x is greater than 9? Now we know that the exponential distribution follows the memoryless property. What is that? P of x greater than s plus t, given x greater than t, is actually P of x greater than s. So therefore, if I follow that, it is basically x is greater than 1. How I got it? Using the memoryless property. Right, so we know that it follows, so easily we got, so this conditional probability, we got it as very easy calculation, p of x greater than 1. And if you just calculate it the same way as we done in the first part, it is e power minus 1 by 2. We got the answer. So memoryless properties of this random variable help us to reduce the calculation effort. I hope you enjoyed. You understand this, how we have done. Yes, this is what we have already done. You may take a snap of it. Now we have another interesting problem related to the memoryless property only, that we can apply memoryless property to do this problem as well. How we can do it? Let x denote the time between detection of a particle with a Geiger counter, and assume that x has an exponential distribution with parameter lambda equal to 1.5. Then the probability that we detect a particle within 30 seconds of starting the counter, p of x, 30 seconds means 0.5 minutes, right? Because x counts in minutes, right? So lambda equal to 1.4 in minutes. So x count its minutes. So therefore, one example, this problem already given, that the probability that we detect a particle within 30 seconds of starting counter, it is P of x greater than x less than 0.5. 30 seconds means a half minute. And this is the cumulative distribution function. If you apply, it is f of 0.1, and we know that 1 minus this, already this things is given. Now what you have to do in this calculation, all units covered into minutes. Yes. So why this example it is given, that you have to calculate that everything into in units into minutes, right? Now suppose that we turn on the Geiger counter and wait 3 minutes. So this Geiger counter is actually a machine that counts this kind of measurement. So now suppose we turn this counter and wait 3 minutes without detecting a particle. So we wait for 3 minutes and we have not got any particle. What is the probability that a particle is detected in the next 30 seconds? Correct? So you have your probability density function because it is randomly distributed. So what is the probability density function? Maybe I can write it first. Fx is equal to lambda e power minus lambda x. So it is in minutes. So e 1.4 e to the power minus 1.4 into x. Whenever we have x is greater or equal to 0 and equal to 0 otherwise, because it is already given. And then if I have this, I know its cumulative distribution function is 1 minus e to the power minus lambda x minus 1.4 times x whenever I have x greater or equal to 0 and equal to 0 otherwise. This is the cumulative distribution function, CDF. Right, now what you have to answer, what is the probability that a particle, first of all, now suppose we turn on the counter and wait 3 minutes without detecting a particle. So this is already done. Then what is the probability that a particle is detected in the next 30 seconds? So it is actually conditional probability you have to, right? So therefore we have to find that this quantity probability of x, what was already given is up to 3 minutes you have not detected particle. So x is already greater than 3. And then you have to find that the particle is detected within next 30 seconds. So 3 minutes plus next 30 seconds. So probability of that you should get the success in less than 3.5 minutes. Given that up to 3 minutes you have not detected the particle. So this conditional probability you have to find. Right. Now this one is, we know that conditional probabilities, that properties, it is actually 1 minus P of x greater than 3.5 given that x greater than 3. So this is the property of conditional probability, that this condition can be same and then this is 1 minus this. So condition, because we know that conditional probability satisfy uh, all properties like the normal probability. So therefore we have this one. Now we know that exponential random variable follows the memoryless property. So I should have, this is actually equal to 1 minus P of x greater than 0.5. Now 1 minus 0.5 is actually P of x is less than or equal to 0.5. And P of x less or equal to or less than, they are the same, we know, but this value, it is already given here, it is already calculated. We can also calculate it, but it is already given. P of x is less than 0.5. So this is actually equal to P of x less than 0.5, and this is already calculated in the question. It is 0.30, right? So again, for this example, we have used the memoryless property, because from here to here we have done the memoryless property, and after that we solve the example very easy. I hope you understand. and I hope you enjoyed. So yes, all this thing we have, all the content of this talk we have taken from these references. I hope these videos are helpful for you. You may give your feedback in the comment. Thank you very much. We'll meet in the next video.